Welcome to The Explainer. Today, we're going to unpack one of the most fascinating, yet completely invisible forces shaping our physical universe, magnetism. Now, if you're a focused learner trying to truly grasp the mechanics behind magnetic fields, well, you are in exactly the right place. We're going to strip away all that dense textbook jargon. Instead, we'll use clear, direct visuals straight from the physics data to reveal how magnetism actually works. We're talking everything from the microscopic dance of individual particles all the way up to the massive scale of the planet we live on.
Okay, let's dive into this with a fact that might completely flip how you look at a globe. So if you've ever used a compass, you know the needle points north, right? But think about it. Because opposite magnetic poles attract, that actually means the geographic north pole of the Earth is, technically speaking, a magnetic south pole. Crazy, right? It's just a fantastic little geographical contradiction to kick things off.
So here's our logical roadmap for today's explainer. First, magnets and Earth's field. Second, visualizing magnetic fields. Third, force on moving charges. Fourth, particles in circular motion. And finally, currents and magnetic flux. We'll start big with macroscopic magnets, dive deep into single particles, and then scale right back up to macroscopic currents.
All right, let's jump right into Section 1, Magnets and Earth's field.
Take a look at this. It shows the Earth acting like one giant bar magnet. You can see the rotation axis, that's true north, and just slightly offset from it is the magnetic pole. Now notice the compass on the left side of the Earth. The north end of that compass needle, the orange part, is being magnetically attracted upwards. Like we just established, since opposites attract in magnetism, the top of our planet is actually harboring a magnetic south pole.
Now, the absolutely crucial point here is that whether we're talking about a whole planet or just a simple bar magnet sitting on a lab table, they operate identically. Magnetic fields can be visualized using these field lines, and as you can see, they are always closed loops. They flow out from the North Pole and curve right back into the South Pole. It's just this continuous, unbroken circuit of invisible force.
Moving right along to Section 2, Visualizing Magnetic Fields.
And this brilliantly illustrates how physicists draw invisible 3D fields on flat 2D paper. When a magnetic field, which we represent with the letter B, points perpendicular to the page, we use some very specific symbols. On the left, you've got a grid of dots. Think of these as the literal tips of arrows coming right at you, straight out of the page. Then on the right, you see a grid of crosses. Think of those as the feathered tails of arrows flying away from you directly into the page. It's a remarkably simple visual code, but it's absolutely essential for everything we're about to cover.
Okay, let's shift gears to Section 3, Force on Moving Charges.
So, the magnetic push a particle feels, it's not just random. It is precisely determined by a few specific factors. Let's break this down step by step so it's not overwhelming. Basically, the bigger the charge or the stronger the field, the harder the push. But here's the kicker. The particle must be moving. If it just sits there, perfectly still, there is literally zero magnetic force. And finally, the angle of that motion really matters. It feels the maximum push when it's cutting directly across the field lines, and absolutely no push at all if it's moving completely parallel to them.
Now, what's really interesting about this slide is how these variables interact in three-dimensional space. We've got a positive charge moving along that red velocity vector v, cutting right through the green magnetic field vector b, and the resulting magnetic force, that tall blue vector labeled F sub b, it doesn't push the particle forward. It doesn't push it backward either. It pushes it perfectly perpendicular to the plane formed by both the velocity and the field. It's a completely sideways push, which is a massive defining characteristic of magnetism.
Oh, and there is a quick but super vital rule to remember here. If we swap out our positive charge for a negative one, like an electron, say, moving in the exact same direction through the exact same field, that sideways force completely flips. It points in the exact opposite direction.
Before we go any further, let's quickly define our measurements. The standard unit for measuring a magnetic field is the Tesla, written as a capital T. Technically, it's defined as 1 Newton of force per coulomb of charge moving at 1 meter per second. You'll also hear about a smaller unit called the Gauss. To put it in perspective, it takes 10,000 Gauss to equal just 1 Tesla. So yeah, a full Tesla is seriously powerful.
Next up, let's look at the physical consequences of all this in Section 4, Particles in Circular Motion.
Because this magnetic push is always acting sideways, it acts exactly like a tether, forcing the moving particle to curve. And if the speed and the field are constant, well, the particle gets trapped in a perfect circular orbit. Let's walk through this derivation. By taking Newton's second law of motion and balancing it with our magnetic force, we can actually mathematically predict the exact radius of this microscopic racetrack.
And because this motion is so perfectly uniform, a really beautiful mathematical harmony emerges from the particle's dance. The most incredible takeaway here? The time it takes a particle to complete one full loop has absolutely nothing to do with how fast it's going. No way, right? But it's true. A faster particle simply carves out a wider radius, meaning it arrives back at the starting line in the exact same amount of time. It's just so elegant.
All right, let's scale things back up for our final section. Section 5, currents and magnetic flux.
So remember how we've been talking about individual moving charges? Well, an electrical current is ultimately just a river of those exact same charges moving together through a conductor, like a wire. Because every single moving charge in that wire feels that sideways magnetic push, the entire wire gets pushed. The total magnetic force really just comes down to the amount of current, the physical length of the wire, and the strength of the magnetic field it's sitting in.
Now, we need a way to measure not just the strength of a field at one specific point, but how much of a field is actually passing through a given space. We call this magnetic flux, and it's measured in a unit called the Weber. You can kind of picture it like rain falling through a hula hoop. The flux depends on three things: the strength of the magnetic field, B, the size of the area, A, and the angle theta at which the field pierces that area. If the field hits perfectly perpendicular to the area, you get maximum flux. But if it's parallel, just slipping straight along the edges, zero flux.
Look, if you take away only one core concept from this entire explainer, let it be this. Magnetism is, at its fundamental core, just the mechanics of moving charges. Whether it's an electron trapped in a tiny circular orbit in a lab, electricity flowing through the copper wiring in your house, or all the way up to the molten iron churning inside the Earth's core to create our planetary poles, the whole shebang is driven by the simple, elegant rules of moving charges interacting with fields.
Which leaves us with a final, slightly mind-bending thought. As you sit there right now watching this explainer, Earth's magnetic loops are passing right through your body. The electrical wiring in your walls? It's creating its own subtle fields too. So how much invisible magnetic flux do you think is quietly passing through the area around you at this very moment? The math is always there, continuously operating in the background, shaping our physical world in ways we can't literally see, but can entirely understand. Thanks so much for diving into the mechanics of magnetism with me today. Keep wondering, keep observing, and as always, keep learning.